Okay, so we're going to look at two exam questions from the new specification, and we're going to just dive straight in with them. So this one says, given that f of x equals e to the 2x cos x, show that the second derivative, f double dash x, is equal to p f of x plus q f dash x, where p and q are integers to be determined. So I'm going to start off by differentiating f of x and then differentiating it again. So we have that f of x is equal to e to the 2x cos x, and I'm going to need to use the product rule here. If I differentiate the first part, which is e to the 2x, I get 2e to the 2x, and then I leave the cos x. I'm then going to keep the e to the 2x the same, and I'm going to differentiate the cos x, which goes to minus sine x. Now what I'm going to need to do here is I'm going to need to use the product rule on this bit for the next section, and then I'm also going to need to use the product rule on the second bit here again. So I'm going to start off by doing the product rule on this first bit to find the second derivative. So the product rule here, I've got 2e to the 2x. If I differentiate that, I would get 4e to the 2x, keep the cos x the same. And then I'm going to keep the 2e to the 2x the same, and I'm going to differentiate the cos x, which is going to go to minus sine x. So I'm also going to change that from a plus to a minus. Now I'm going to do the product rule on the second bit. So really it includes the minus there as well. Well, if I differentiate minus e to the 2x, I will get minus 2e to the 2x, and I'll have the sine x. Then I'm going to keep the minus e to the 2x, and I'm going to differentiate sine x to get cos x. So when I then simplify all of this, the cos x bits that I've got, I have the 4e to the 2x minus, sorry, the 4e to the 2x cos x minus e to the 2x cos x, which is going to be 3e to the 2x cos x. And then for the next part, I've got minus 2e to the 2x sine x minus 2e to the 2x sine x, which is minus 4e to the 2x sine x. And so this is what the second derivative is equal to. But they've got this weird thing here where they want us to say it in terms of f of x and of f dash x. So what I'm going to do is I'm actually going to take this whole line here and I'm going to try and replace all of these bits, the f double dash x, the f of x, and the f dash x. I'm going to replace them with the e to the 2x sine x, e to the 2x cos x kind of thing that we've got. So I'm literally going to be rewriting this line. I'm going to do f double dash x equals p f of x plus q f dash x. So f double dash x is 3e to the 2x cos x minus 4e to the 2x sine x. Then I have p multiplied by f of x, which is e to the 2x cos x. And then I have q multiplied by f dash x, which is 2e to the 2x cos x, minus e to the 2x sine x. And I'm going to try and find out what p and q could be. So some people will just be able to spot this straight away. They will spot that the only place where you get the sine x has only got stuff to do with q. So I'm hoping some of you might be able to spot already that q has to be 4 in order to get these bits, and then we can figure out what p is. But if you find that tricky, I'm going to see if I can show you this in a slightly different way. So I'm going to expand the brackets on the right hand side here. So I have 2q e to the 2x cos x minus q e to the 2x sine x. So it distinctly looks like I've got some bits that are to do with e to the 2x sine x, and it also looks like I've got some bits that are to do with e to the 2x cos x, like I've got here. So I can either compare coefficients, but you might find it helpful to factorize as well. So if I factorize this e to the 2x cos x, I would have p plus 2q, and then I've got minus q e to the 2x sine x. So just highlighting those in the same color as before, I can, by comparing coefficients, I can see that this 3 that I have here, the 3 that goes with the e to the 2x cos x, must be the same as this. So that's p plus 2q must be equal to 3. And then if I look on the separate part that I've got here, and I'm going to go to an orangey color, I've got that this 4 must be the same as q. okay? Because they've both got a negative there. So that means that q is equal to 4 and p plus 2q is equal to 3. So I can now solve that equation because p plus 2q, which is p plus 8, is equal to 3. And so p is equal to minus 5 and q is equal to 4. So what we have here is that f double dash x is equal to minus 5 f of x plus 4 f dash of x, okay? I think it might also be helpful to have what f of x and f dash x are. So I'm actually just going to pull this down slightly because I think I'm going to need them in a second. So we worked out this is e to the 2x cos x, and f dash x is 2e to the 2x cos x minus e to the 2x sine x. So I'm just going to pull that down a little bit further. Great. So that was part A of the question, to do the differentiation. And then it says for part B, hence, find the Maclaurin series for f of x in ascending powers of x up to and including the term in x5, giving each coefficient in its simplest form. So we have got the first, the second, and the third derivative. Well, sorry, we've got the function, the first derivative, and the second derivative. We are going to need to find the third derivative, the fourth derivative, and the fifth derivative. Now, the best thing is this word hence. It means use part A to help you. So I am now going to use this line that I've got here. I'm going to differentiate that to find the third derivative. And the best thing about this is I can differentiate the f of x to just get f dash x. And I can differentiate the f dash x to just get f dash dash x. So easy to differentiate that now that it's written in that function notation. And so the fourth derivative is going to be minus 5 f dash dash x plus 4, differentiating f dash dash, you get f triple dash x. And then for the last one, the fifth one, I'm differentiating this term just above it, so it's going to be f triple dash. And then I'm going to differentiate this one here, so it's going to be f with 1, 2, 3, 4 dashes here. And you know, to do the Maclaurin, you need to find out what f of 0, f dash of 0 is, f double dash 0, f triple dash 0, f with 4 dashes of 0, and f with 5 dashes of 0. So we're just going to figure out how we can get these answers and calculating them all. So f of 0, if you put 0 into this expression, you are just going to get 1. If I put 0 into this expression, I would get 0. So I'm just going to get this part, which is going to give me 2. Now this is where it gets interesting, because f double dash of 0 is going to be minus 5 f of 0 plus 4 f dash of 0. So that's minus 5 times 1 plus 4 times 2, which is minus 5 plus 8, which is 3. Now the next one is going to be minus 5 f dash of 0 plus 4 f double dash of 0. Well, that's minus 5 times the 2 above it that we have here, plus 4 times this one. So it's minus 5 times this one, plus 4 times this one. That's minus 5 times 2, plus 4 times 3, which is 2. Now I'm wondering if you can just spot the pattern, and we can just kind of go straight in without that notation. So it's going to be for this one, minus 5 times the double dash, which is 3, plus 4 times the triple dash, which is 2. So that's minus 15 plus 8, which is minus 7. And then for the fifth derivative, it's going to be minus 5 times f triple dash, which is 2, plus 4 times f with 4 dashes, which is minus 7. So that is then minus 10, minus 28, and it is minus 38. So you've got these patterns of how it's relating to the previous derivatives. So all that's left is to say that e to the 2x cos x is approximately equal to, using these numbers that we've got here, the 1, 2, 3, 2, minus 7, and minus 38, 1 plus 2x plus 3x squared over 2 factorial plus 2x cubed over 3 factorial minus 7x to the power of 4 over 4 factorial minus 38x to the power of 5 over 5 factorial. So when I simplify all of these coefficients, I have 1 plus 2x plus 3 over 2x squared. 2 over 3 factorial is just 2 over 6, or 1 over 3. And then I've got 7 over 4 factorial. 4 factorial is 24, so it's just going to stay as 7 over 24. And then this last bit, I've got 38 over 5 factorial. 5 factorial is 120, so I have 19 over 60. So I get minus 19 over 60, x to the power of 5. So this little trick over here of in part A of the question, I'm getting it to write you like this, means that you can then do the differentiation really easily. And you can also do the substitution by noticing that the patterns are, you're doing 5 times the value of the derivative 2 before, plus 4 times the value of the derivative of the one before. And you spot all those patterns, and you come up with all of these coefficients, 1, 2, 3, 2, minus 7, minus 38. And you see them pop up here, 1, 2, 3, 2, minus 7, minus 38. And then they simplify to that bit there for the Maclaurin expansion. Now, this was the first question in the exam paper, so hopefully that wouldn't have put too many people off. I think it would have been much nicer if they said, show that it is equal to minus 5. Oh, sorry, is it 5 or minus 5? Yeah, minus 5 plus 4, and then you could have at least done part B anyway. But for the first question in the exam paper, I think that's pretty nasty. Okay, we're going to try one more exam question, and this one is written like this. So you might like to have a go, see how you do. Okay, so we have a function, and it's ln of 1 over 1 minus 2x, and it wants us to find the first, second, and third derivatives. Then it wants us to find the series expansion about 0 in ascending powers of x up to and including the term x cubed, which is good because we've got 1, 2, 3 derivatives. And then it wants us to do an approximate value for ln of 3 over 2. So our function is y equals ln of 1 over 1 minus 2x. And I guess you need to think to yourself, does that look fun to differentiate? And I don't think it does, so I probably would like to manipulate this using my log laws. Now, using my log laws, I know that this is going to be the same as ln1 minus ln of 1 minus 2x. But ln1 is equal to 0, so it's just the same as y equals minus ln of 1 minus 2x. Now, if I want to differentiate this actually differentiates pretty nicely. So I have, with my blah notation, this is minus ln of blah, which I know is going to go to minus over blah, times by the derivative of blah, which is minus 2. So I just get 2 over 1 minus 2x, or 2, 1 minus 2x to the minus 1. So that's just a chain rule differentiation that I've got then. I'm then going to do the second derivative, and so I'm going to have 2 multiplied by the power, which is minus 1. I'm then going to multiply by the derivative of what's in the brackets, which is minus 2, and I'm going to decrease the power by 1. So I end up with 4, 1 minus 2x to the minus 2. Now, interestingly, it stays positive because the power was negative and the derivative of the function inside the function was negative. So you actually just end up with it remaining positive, and that pattern is going to continue when we go on to the third derivative here as well. So I'm going to have the 4. It's going to multiply by the minus 2 from the power and the minus 2 from the derivative of 1 minus 2x. So the negatives are going to cancel. You're just going to have 4 times 2 times 2, 1 minus 2x to the power of minus 3, which is just 16, 1 minus 2x to the power of minus 3. And that is part A of the question because we have done all 3 of the derivatives. Part B of the question wants you to find the series expansion of it It doesn't actually even use the word Maclaurin, but we know it's going to be a Maclaurin series, Maclaurin expansion here, and it only wants us to go up to x cubed. So I'm actually going to put part B of the question running alongside it here. One of my students asked me, how do you show that you're going to be substituting x equals 0 into something like dy by dx, second derivative? Well, you can do a line and you can write x equals 0 like this, and you can do that for all of them. But probably what I'm going to do here is I'm just going to say when x equals 0, and I'm going to find out what y is equal to, etc., etc. Well, when x is equal to 0, the whole thing is going to be ln of 1 or minus ln of 1, which is just 0. When I do dy by dx and I substitute 0 in here, well, I've just got 1 to the power of anything, which is 1, so it's just going to be 2. When I do the second derivative here, again, this is just 1 to the power of something, so it's just 1, and it's going to be a 4. And then in a similar logic, that third one that we've got there is just going to be 16. So this means that the expansion is going to be that ln of 1 over 1 minus 2x will approximately be equal to, well, there's a 0 at the beginning, so there's not going to be anything. It's just going to be 2x plus 4x squared over 2 factorial plus 16x cubed over 3 factorial, which we want to simplify to 2x plus 2x squared, and 16 over 6 is 8 over 3x cubed. And so that is the simplified version of the expansion up to and including the term x cubed. Part C of the question says, use your expansion to find an approximate value for ln of 3 over 2, and it wants you to give your answer to 3 decimal places. Okay, so we're going to be using what we've just done in part B of the question, and it wants us to find ln of 3 over 2. So we've actually got an expansion for ln of 1 over 1 minus 2x, and we want to try and find out what ln of 3 over 2 is. In other words, I'm going to try and find out what value of x will make this bit that I've highlighted in yellow here equal to 3 over 2. So I'm going to ignore the ln's, and I've got 1 over 1 minus 2x is equal to 3 over 2. If I multiply this side by 2, if I cross multiply, I'm going to get 2 equals 3, 1 minus 2x. So 2 equals 3 minus 6x. 6x equals 1, or x equals a sixth. And just to check that what we've actually done there, this actually does make sense, because if I were to substitute x equals a sixth into 1 over 1 minus 2x, I would have 1 over 1 minus a third, which is 1 over 2/3, which is indeed 3 over 2. Okay, so you don't need to show that because we've already solved it. So this means I'm going to take x equals a sixth and I'm going to substitute it into the expression. So ln of 3 over 2 will approximately be equal to 2 multiplied by a sixth plus 2 multiplied by a sixth squared plus 8/3 multiplied by a sixth cubed. And I probably use the answer button for this on my calculator. So let's just move this across so I can actually see the whole thing. Okay. So I would do a sixth on my calculator, and I'm going to store that as the answer. So it's just going to be 2 answer plus 2 answer squared plus 8 over 3 times by the answer cubed. And we get 65 over 162. We want it as a decimal, and they want it to 3 decimal places, so it's 0.401. 0.401 to 3 decimal places. And that's the question over, but what I would want to do is I would want to find out, well, how close is it? So I'm actually going to find out what ln of 3 over 2 is actually equal to, and it will kind of tell me if I've got the whole question correct. So if I do the ln of 3 over 2, we should get something close, and we get 0.405 to 3 decimal places. And the good thing about this is really close. which is good. If we wanted to make it even closer, we could have used more of the expansion. And that's about it, really. If they ever want you to increase the accuracy, then you can just use more of the expansion. So there's a couple of good questions there. There's some nice ones in the mixed exercise and the review exercise too. But hopefully you found these exam questions useful.